Hi, I'm Andreas. Today I want to talk about how to understand quantum dynamics geometrically. I will assume that you are familiar with basic quantum physics and you're making your first steps in quantum dynamics, and maybe you want to find out more about how it all works. So let's start from the time-dependent Schrödinger equation that you are well familiar with and introduce notation. I will be using h bar equals 1. We're usually using atomic units in implementations, so this is actually what we do. We have I d over dt. The time derivative of the wave function equals the Hamiltonian applied to the wave function, and we know that we can use this. We can solve this formally using the exponential operator e to the minus I h t applied to psi at the initial time 0. And evaluating this exponential is kind of difficult, especially because the Hamiltonian consists of the kinetic and the potential operators which do not commute. So typically, one of the first ways to solve this that you learn is the split operator, and I'll be looking at that today. So the split operator prescribes that we are making a small time step delta t, and we are obtaining the wave function after that time step by making half a time step along the potential, a full time step with a kinetic operator, followed by another half time step, b delta t. And actually, as you know, this should be applied from right to left. So first we apply this one, then this one, then this one. And it can be shown quite easily by comparing this to the Taylor expansion of the exponential, that this is a third order method in time, in the time step. So this is already quite accurate. So let's try to understand what applying this operator actually means to see if we can understand how this actually works. So let's think about a problem where we have maybe a diatomic molecule, or we have a molecule approaching a surface. This is the potential. And we have some initial wave function that has a Gaussian envelope, and this expectation value is x0, so that we can write psi of t equals 0 equals normalization factor times e to the minus x naught squared over 4 sigma squared, because this is the square root of the normal distribution. And we want this to have some initial momentum moving towards the barrier, for example, a molecule colliding with a surface. So we're going to say this is modulated by a plane wave e to the ip, where p is the momentum, x minus x naught. Let's draw a plane wave like this so that we can talk about this later. So if this is the complex plane, sorry, this is the real part, and this is the x coordinate, then moving in a positive direction, so moving to the right in the coordinate system, requires us to have a spiral in the mathematically positive direction, which is counterclockwise. So the wave function looks like this. And that corresponds to a momentum to the right. So let's say this initial wave function is moving to the left, so we need to move, we need to rotate in the clockwise direction. So we have this, where the dotted lines are behind the real part equals 0 plane. So let's see what this looks like if we zoom into an infinitesimally small region around x naught and make a diagram like this in the complex plane. So again, here's the real part of psi, here's the imaginary part of psi. This is the coordinate axis right here, and this is x naught. Now our potential, if we zoom in really far, almost looks like a line, like so. And our wave function is almost like a plane wave. So if this is psi of x naught here, we're moving a little bit in the clockwise direction. I'm sorry, in the counterclockwise direction as we go to the left in the coordinate system. So this is psi of some x to the left, and this is psi of x naught here. So now what happens if we apply this operator? This exponential is a rotation because we have an imaginary exponent. So we're using v times delta t over 2 as an angle. And we know v of x naught is this number right here. This here is v of x naught. So we rotate to the negative direction, so that is clockwise. So we're rotating by a bigger number here. And if we go to the left, the potential becomes somewhat smaller, so we rotate clockwise by a smaller amount. Which means that we have now amplified the twisting of this plane wave that the wave function already had, so we've accelerated the wave function to the left, which is exactly what we expect as we move down this hill in the potential. So let's try to quantify this. So what we have is an existing plane wave modulation of our Gaussian. So let's look at this term right here, how this changes. So we have, let's call this angle here capital phi. And so phi of delta t after delta t over 2 after applying this half time step is going to be the phi that we had before, p of x minus x naught. And now we're subtracting v times delta t over 2. So minus v of x times delta t over 2. So now let's bring this into a form that we can understand. Specifically, we want to have something times x minus x naught so we can see how the momentum changes. So we're going to say p x minus x naught minus v of x minus v of x naught times delta t over 2. This is a plus v of x naught, so we have to subtract v of x naught delta t over 2. And this is just a constant phase, which does not change the quantum state, so we can safely ignore that. And this is now equal to p times x minus x naught minus, let's get a factor out like this, v of x minus v of x naught over x minus x naught times x minus x naught delta t over 2 minus this constant phase here. And this means that we have changed the momentum by v of x minus v of x naught over x minus x naught times delta t over 2. Now we looked at an infinitesimally small region here. So this is the gradient of the potential. So we can say that P of delta t over 2 equals P naught minus gradient of the potential times delta t over 2. And this is, in fact, the momentum change that we expect classically. Now, if we apply the kinetic part of the operator, we just have wave functions coasting in free space. There's no potential here. So this is just the propagation of some Gaussian that we know as a free particle. So what we get is x of delta t equals x of time 0 plus p over m times delta t. And this is in fact just Newtonian mechanics. And then finally we do another half time step and we get p of delta t equals p of delta t over 2 minus the gradient of v delta t over 2. So when you look at these three equations and perhaps substitute this equation in here to see better how this corresponds to something that you know, then you'll see that taking these three equations together corresponds to the Velocity Verlet method in classical dynamics. So we have successfully related quantum dynamics using the split operator method to Velocity Verlet, which is also a third order method, as you know, simply by looking at how this operator changes the phase of the wave function locally and transforming the change in momentum to an expression that we can use like this as the gradient of the potential. And now you can also understand why here we're using the potential in the exponential rather than the gradient. So I hope this was useful to everyone. If you would like to know more about how to make this step with the free particle, I will probably produce a separate video for that so that we can have a solid footing for everything here. Hi, I'm Andreas. Hi, I'm Andreas. Hi, I'm Andreas, and this is some sample text. For example, the time-dependent training equation. EDSE I d over dt psi equals h psi. Now I want to see if that's big enough to read in the camera.